Hello everyone, I'm Hannah and I'm going to walk you through a couple of examples for work energy chapter. The learning objectives of this presentation are to help you identify work energy questions and try a couple of challenging problems. In the first example, there is a block that has a mass of 1.2 kilogram and moves within the frictionless vertical slot. The block starts from rest when the attached spring is in the unstretched position at point A. And we want to find the constant vertical force F, which must be applied to the cord so that the block attains a speed of 2.1 meter per second when it reaches SD equals to 0.2 meter. This is the final position of the block, and these are the known values. So because the problem is asking us to find the force in order to reach certain velocity over a certain distance, we know that it's a work energy problem. So this is how you identify work energy problems. To solve this question, first we need to calculate the displacement of the force. So the initial length of the cord, here shown as cord A, can be calculated as the square root of LA to the power of 2 plus W to the power of 2. The length of the cord after the block reaches SD is shown as cord B and can be calculated as the square root of LA minus SD to the power of 2 plus W to the power of 2. The displacement for force F equals to cord A minus cord B. Using the principle of working energy equation, we have the initial kinetic energy plus the work that's done by all the external and internal forces acting on the system is equal to the final kinetic energy of the system. Here, the initial kinetic energy of the system is 0 because it starts from rest. So we have the work of the force, which is force times the displacement, plus the work of the gravity, which is minus m times g times sd, plus the work of a spring, which is minus 1 over 2 times k times sd to the power of 2, and that's equal to final kinetic energy, which is 1 over 2 times mass times velocity at point B to the power of 2. And if we solve this equation, we obtain F as 49.3 newtons. In the second question, a block of 1 kilogram rests on a smooth semi-cylindrical surface. So on this surface. An elastic cord having a stiffness of K equals to 6.165 Newton per meter is attached to the block at B and to the base of semi-cylinder at point C. If the block is released from rest at A, find the unstretched length of the cord so the block begins to leave the semi-cylinder at the instant theta 2 equals to 45 degrees. This problem can be a little bit tricky to visualize. I just want you to note that the spring will displace the block along the semi-cylinder surface, here shown as the green line. So because all the forces are conserved, we can use the conservation of energy directly in this question. So the initial kinetic energy plus the initial potential energy is equal to the kinetic energy at point B plus the potential energy at point B, where theta is 45 degrees. So the initial kinetic energy is 0 because the block is released from rest at point A. The kinetic energy at point B is 1 over 2 times mass times velocity at point B to the power of 2. In order to find the potential energies at point A and point B, we need to find the length of the spring at these 2 points. The length of the spring at point A is pi times A. It's the circumference of a half a circle. If we assume that the unstretched length of the spring is delta, then the potential energy at point A is 1/2 times k times pi A, so the length minus the unstretched length, which is delta, to the power of 2. The length of the spring at point B is pi A minus the length from A to B, which is pi times A over 4. So the potential energy of the spring at point B is 1/2 times k times pi minus pi over 4 times A. So the length minus delta, which is the unstretched length, to the power of 2. The gravitational potential energy at point B is m times g times A times sine of theta B. Looking at these equations, we realize we have 2 unknowns, so delta, the unstretched length, and then VB, the velocity of the block, but only one equation, so only the conservation of energy and 2 unknowns. But because we know that the block begins to leave the semi-cylinder at point B, we can write a force balance equation in order to eliminate one of the unknowns. So here I'm drawing a free body diagram for the block. You can see the normal and tangent axis. And because the block is leaving the surface at this instant, the normal force is 0. And I'm writing the force equation in normal direction, which is mg times sine of theta b equals to m times the normal acceleration, which is velocity at point B to the power of 2 over radius, which is a. And then using that, we can obtain the velocity at point B based on the known values. We can substitute this velocity in the conservation of energy equation and eliminate the velocity term as shown here. So here we have one equation, and the only unknown that we have is delta. We eliminated the v term, we substituted the velocity, so the v term was eliminated, and we only have the delta to solve for. And solving the equation, we obtain delta as 0.6 meter. In conclusion, you need to carefully read and think about the terms in the question. For example, for the first question, we saw that the displacement of the force is not the same as the block. In the second example, we saw that we can get the missing equation using force equation. Also, visualization is very important for understanding the questions and solving it correctly. As a final note, we encourage you all to use SMath or MathCAD for solving dynamic questions. And the solutions for these examples here were done in SMath and MathCAD. Thank you all for listening to this presentation.